and they're all 0. So that torus that we were talking about before, what would that look like? Well, that's just a bunch of links. They're not capped. They're put in a cycle. Which is why these are 0. What's the next step, you ask? Well, there are 2 ways this could go. One, it's how do we add more holes? If you wanted a double torus, like a figure 8 thing. Again, by analogy, you go with our one-dimensional example. You have a connector thing. Let's see if we can break this down as much as we can. Well, this looks like, so we have one guy that looks like that, and then there's another link, and then there's another link, it's just facing another way. This guy, well, that kind of looks like a link, except we already counted this point in the center. So we get ourselves something that looks like that. Never seen that before. What would that be? Well, I think it's another kind of cap, a special kind of cap, and what's its Euler characteristic? 0 points minus 1 edge. So these guys all have link, 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 link. The only thing that's an auto link is this guy. So a figure 8 graph of just vertices and edges has an Euler characteristic of -1. And more things like that happen. So similarly, stuff like that happens for stuff in more dimensions. Examples of the dimensional. No, I can't make it sound smart. So it wouldn't necessarily always be -1. So just like in our one-dimensional example of paths and cycles, we only needed one cap. So one cap, and so its Euler characteristic of a path would be 1. But for the 3-dimensional, 2-dimensional sort of idea, you need 2 caps. There are 2 different sorts of caps, so they both have the same Euler characteristic, so it was 2. So that's something else I haven't quite gone into yet, is how many caps would you need, what kind of caps what sort of caps exist for making different sort of cycles. So this is, these are 2 cycles stuck together, or paths. So here you can stick on even more links and make something interesting. You know, this would look like a figure 8 with a tail. But I know that this has the same Euler characteristic as just a figure 8, because these were just links added on. I don't know if you've heard of trees. Those are, again, just a bunch of links, but with one cap. So they're like a special sort of path. In fact, that would work for your ball shapes too. So say you had something that kind of looked like a Y, a three-dimensional Y. That you could take and into a ball, because it's like a bunch of these kind of links put together. And so one thing would be exploring different shaped links, like links that have different shapes at either end. Again, hint, it's still 0 because one edge is dotted. So this, if I wanted one that was a square on one side and a triangle on the other side. I'm going to draw this. So you can connect that there, that there, and then this comes out and connects here. So we still have 4 faces because of here, and then we have all the 8 lines, and then so everything still adds up to 0, no matter what the other side looks like. And it should be like that if this were solid and this were dashed. Because you still have, around it, you still have as many faces as you do edges. So they get canceled out. Then this, well, this is a cycle. It has as many edges as it does vertices. So they all go back to 0.